So from at the end of last class, we had, we did this one already. What kind of problem is this one?
Binomial.
Yeah, binomial. So we had, that's where the probability of x is equal to n choose x times little p to the x times little q to the n minus x. So we did this one already. And we had 8 choose 2 times 0.32 to the second times 0.68 to the number. So 2 successes means we have 6 failures out of 8. And you guys got 0.2835?
Yes.
Great. And then less than 3 means, less than 3 means you either have 2 people or 1 person or 0 people. So you find all of those and then add them up because it's 0 or 1 or 2, and ors we add. Great, you guys are doing great. Nice and loud for her to perform.
Awesome.
So probability that x is 1, we'll do 1 first, is 8 choose 1 times 0.32 to the 1 times 0.68 to the 7, and that was 0.1721. 1, and then probability x is 0. And as I was explaining to those guys earlier, I think it's kind of nice about it when it's all or none, then you don't even need to do the binomial. You can just do probability that none of them, like no and no and no and no and no. How many ways are there of having everybody say no? There's only one way, right? So it would just be 0.68 to the 8th power, because 8 choose 0 is just 1, and then 0.32 to the 0 power is also just 1. So really, you can shortcut that, and it's really the same thing as 0.68 to the 8th power, which is 0.0457.
Yes.
I'm actually going to write it over here so I can add them up easier. So when you add them all up, you get 3, 1, 5. You get that, right?
Yep.
Okay, good. So that's your answer. At least one has a college degree. So at least one, I either have at least one sibling or I have at least one sibling or I have none, no siblings. So those are complements. So I can either find the probability x is 1, probability x is 2, 3, 4, 5, 6, 7, and 8 and add those up. Or I can just find the probability that x is 0 and subtract that from 1. So we will just do that instead. I think you guys are all good with that. So this is equal to 1 minus the probability of none, which is 1 minus 0.5013 or 0.4987. Oh no, that's not right. Totally wrong. Totally wrong.
0.0457.
0.0457, which is 0.9543.
Yeah.
Good. Mean, variance, standard deviation, we did it in class, right? Mean is NP, variance is NPQ, and standard deviation is square root of NPQ. Great. So are you guys,
Expected value is the mean in that case then, is what you're asking?
expected value is the mean,
Okay.
always. Expected value and mean are always the same thing. Yeah. So here, this is just a reminder about the whole binomial stuff. Do you guys remember binomials? So if I wanted the probability of getting exactly 2 boys, I could do it by doing boy, boy, girl, right? Or I could do it by doing boy, boy, girl, or I could do boy, girl, boy, or I can get there by going girl, boy, boy. So there's 3 different ways of getting exactly 2 boys. However, they all have something in common, right? They all have 2 boys. So we know when we go along these trees, we multiply all the branches, right? Because girl and boy. So we're always going to have 2.4s being multiplied together and 1.6, no matter what. So we're always going to have our probability of success, little p, 0.4, to the number of successes raised to the 2nd power, and number of little q, 0.6 raised to the number of failures, 1. So that's always going to be true, and this number is going to be the same for all three of them, right? So normally, I could do it, I could get, how always could I get exactly 2 boys, that way, or that one, or this one, or as we'd add. So you can either compute all these and add them, but since they're exactly the same, I can just multiply, there's 3 of them, I can just multiply by 3. Just find this and multiply by 3. Right? So, that's where this is the, so in terms of that formula, this is the little p to the x, and this is the little q to the n minus x, and then the 3, the nc2, is that how many ways, how many of these branches will end up with one of the ones I want. So that's that. That's the NC2. NC2 is 3 in this case. Right? Or I should say n choose x is 3 in this case. Cool. All right. So just as that's a quick reminder of binomial and where that comes from, so people are all good with that. I think you guys, have you guys done this one yet? Not all of it? You started on it, or you didn't start on it?
We started on it.
Okay, so take another minute or 2 and do this one.
Did you say not to do number 8 because we don't need to know it for the test, or because we're coming back to it?
Yeah, really, it's not that important. But I was going to take a look. So the first part is z-scores, right? Those are pretty straightforward. How far something is from the mean. So you guys were good with that part?
Yes.
So you did, the first z-score was, you did 560 minus 690 divided by 0.96.
Yes.
And you got negative
1.35.
1.135?
Oh no, I just got
Just 3.5.
3.5.
1.35?
Yes.
Yeah.
Okay. And then the second one, you got 780 minus 690 over 0.96, and you got
0.9375.
375. Okay, good. So then this one here, what if we draw a picture? That might make it easier. So draw a picture. I want to know from 560 to 780. And I want the area. It's normal distributed, right? So as soon as you see normal distributed, you know it's going to be one of the normal curves. So do you guys remember how to find the area between 2 points on a normal curve? How do I find the area from here to here? Maybe we'll do a quick review. So this is, this kind of might help you guys out. So if I give you an x value, and I want to find the area or the probability, area is probability, first you convert your x value to a z-score, and then you use normal CDF of those z-scores to find the area between them. Here we're going to do, so our z-scores here were negative 1.35 and 0.9375, and these are the z-scores. These are the x values. So we're going to do normal CDF of what?
Negative 1.35.
Comma 0.9375.
0.93.
What did you guys get?
Should be under second bars.
Second bars, yeah. So everything you need is either going to be under second bars or stat tests, maybe stat edit. Stat calc for that one thing.
Got 0.737.
737? Okay, good deal. And then explain what that means. What does this mean in context of the problem? In context of, so what does 0.737 mean in the context of entrees? there is a
73.7% chance that you get an entree in between those costs.
yeah, between 680, that you ran pick an entree and it'll cost between 560 and 780. What's another way of putting it?
73.7% of entrees cost between 560 and 780.
Yep, those are the two ways of doing it. Good. So the probability that you pick an entree and it'll be between those is that, or 70% of them are between that. Good. All right. Nice. So I think the one we're going to do next after that is, we're skipping 8, we're going to go to 9. So for 9, why don't you guys do the second part first, and then the first part last. So do the part where it's just one rat. Oh, and cross out the word mean. So here we're talking about just one rat. So it's very similar. First thing you need to do, you have a x value, or your picture. Means here, 112's there. I want to find the probability that someone's less than that. So first I need to find the z-score for him. So his z-score is going to be 112 minus 115 divided by 16, and you guys got
Negative.
0.1875.
Yeah.
0.1875.
Yeah.
Yes.
So negative 0.1875. And so you want to find that area. You do normal CDF of what's my left area? What's the left z-score of this area here?
Negative 999.
Yeah, negative 999. And if you have a, so check yourself and make sure you didn't get, I don't even say it. Negative 999, comma, negative 0.1875. What did you guys get?
0.42?
Yeah.
56?
Yes.
0.4256.
4256. Okay, if you didn't get that, or you got something else, make sure you didn't put in, a lot of times people want to put a, did you get the same thing?
She couldn't get her calculator to compute it.
I put the minus sign
Oh.
for the
You gotta leave the mean is 0,
Oh.
standard deviation is 1, and then you're good. Leave those alone.
That's
And
why I
then
keep
you're-
saying
and then you're-
error.
and then you
I'm
got it.
confused.
Yeah.
That's weird.
So yeah, leave your mean at 0 and the standard deviation at 1. Now, we're going to look at the second part of, the first part of this, which is now we're talking about 36 rats and the average of 36. So you got to remember Steph Curry, right? Are you guys okay with basketball?
Yep.
Or do you want a different kind of?
That's cool.
Okay. What's the probability that he has a big game, he has a 45, I pick a game and it's a 45 point or more game? Could happen, maybe 10%, 15%. But what's the probability I grab 36 of his games and average them? His average is 30 points. Or shoes, are shoes better?
Sure.
It's whatever.
Are you better at shoes? What's something you like?
Me?
Yeah.
I don't.
Or
I don't
something
know.
you're comfortable with in terms of how much things cost or how much they are.
Oh. I don't know.
Face masks.
Oh.
Something with some variance.
Gas.
Gas.
Yes.
Okay, great. So that's a good one. So say I randomly pick a day in the last 5 years. What's the probability I pick a day and the cost of gas at Costco was more than $4? It could happen, right? Maybe 5% chance, something like that. What's the probability I randomly pick, but it's usually around like 350, something like that, 370, 380. Say the average is 360. What's the probability I pick 36 different days in the last 5 years, and their average is more than $4? When only 5% of the time is it more than $4. You guys
Right.
kind of see what I'm saying?
Mm-hmm.
Or pick something even better, like 280 or less. How often has that happened in the last 5 years? Very rarely. It's happened, right? So it could happen, but I'm not going to pick 36 days and have the average cost be $2.80 or less. So you guys see what I'm
Right.
saying? If I average a bunch of them, because if I happen to hit a couple lucky days, I'm going to hit some unlucky days where it's 390, and those are going to balance each other out. So that's the idea of the central limit theorem, is that when you pick an average of 36 or an average of some number, then your standard deviation isn't gonna be like this. It's not gonna be like that. It's gonna be like this, right? It's gonna be, your range of them is gonna be here instead of your range being out here. Remember, standard deviation measures your range. So it's gonna be a lot smaller range. So instead of using the standard deviation sigma, we're gonna use the standard deviation for a sample mean, because this is a mean of 36. We're not talking about one guy, we're talking a mean of 36. So instead of using, what's the symbol used for sample mean?
Mu? No, wait.
X bar.
Yeah, X bar.
So instead of using mu, we're gonna use sigma, instead of using sigma, we're gonna use sigma X bar.
Yeah.
What's sigma X bar equal to? Anybody remember? The old standard deviation divided by square root of n. So everything else is the central limit theorem, right? Central limit theorem. Everything else is exactly the same as you just did a second ago, only instead of using the regular sigma, you're going to use sigma x bar. Instead of using 16, you're going to use 16 divided by square root of n. So why don't you guys go ahead and work on that one. All right, so let's take a look at this one. So it's going to be exactly the same. All right, we still have our little picture. Here's our middle. Here's 112. Or what, less than 112. So again, we still have to find the z-score. How do we find the z-score? We do 112 minus our mean, 115. Only we're going to divide by
The new standard.
the new standard deviation, which is going to be 16 over square root of 36, which is 2.67, I think.
Yeah.
And you guys got what?
Negative 1.124.
So then, when you do normal CDF of that, we'll do normal CDF of, what's your left z-score?
Negative 999.
Negative 1.124, and you're going to get this time, what'd you get?
131.
131?
Yeah.
Great. So it's a lot less, right? It's a lot smaller because your z-score is a lot larger. Or more negative, I should say.
Yeah.
Cool. What's the next one? Number 10. Do 10.
Cool.
Alright, so this one's, you could use binomial. This one's even easier than that. Whenever you have all or none, it's super simple because how many ways can I have 5 people and pick all of them? There's only one way, right? So then it's like, you know, what's the probability that she works part-time?
42%.
And she works part-time. What's
Time.
probably you work part-time? What's probably I work part-time? 40%. So what's probably she does, and you do, and I do, and we multiply. So it's just going to be 0.42 times 0.42 times 0.42 times 0.42. Right, the alls and the nones are super easy. So what did you guys get for that one?
0.0311.
Great. Is that likely or unlikely?
Unlikely.
Unlikely. Why?
It's
Because
less than
it's less than
5%.
5.
Less than 5%. Good. Now, what's probably that none of them works part-time? So it means you pick someone and no, they say no, they say no, they say no, and they say no. Remember, the alls and the nones are easy. What do you guys get for that one? So what's the probability that she does not work part-time?
58%.
Great. And what's probably she does not work part-time?
58%.
What's probably you don't work part-time?
58%.
So it's probably that she doesn't, and you don't, and this other person doesn't?
0.1132?
0.58 to the fourth power. Yes, which is, what'd you say?
0.1132.
Good. Now, what a lot of people got confused about was they were expecting this question. They're expecting at least one. So what's the probability that at least one works part-time. So yeah, so the alls and the nones are super easy, straightforward. It's the at least one that's that strange one minus none. Either you have at least one person working part-time or you have no people working part-time. So do you guys want 10 seconds to sort that one out? Or you already have it? Alright, so this one is 1 minus probability of none. Which one was none?
1, 1, 3, 2.
Yep. So 0.8868.
6, 8.
Great. 8 is great. 11? Do you remember 11?
Oh my.
This. What kind of problem is it? How many? It's a how many
Yeah.
problem, right? So it's not probability. It's in the probability area, but it's not really probability. It's, anybody have an idea?
I
forgot
don't
what
work
they call
for
it.
It's a counting problem.
Counting.
So can you reuse people or not reuse people?
Cannot.
Cannot. So it's going to be either permutation or combination.
Mhm.
So permutations are the regular ones. This times that times that. It's when order matters.
Mhm.
Combinations are kind of that weird one. One of my students calls it chaos because it's a C. So when it's a C combination, she thinks that it's chaos because its fractions are chaos. So it's like chaotic. It's when you have to divide out the duplicates. So it's not the normal thing. Or you can think of like chaos, like there's a whole bunch of them bouncing around and all wherever, not in their set spots. So which one is the first one? Is it a permutation, where order matters, or is it kind of more chaotic, a combination?
Permutation.
Permutation.
Mhm.
So it's going to be the regular one. How many spots are we picking?
5,
5. How many options for the first spot?
12,
Because there's 7 men and 5 women. How many options for the second spot?
11,
Next one,
10,
next one,
9,
next one. And what are we doing these numbers?
multiply.
Multiplying.
Multiplying. Good? B is a little bit different. Here they have the same task. So here, does order matter?
Mm-mm.
Order doesn't matter. And the way one of my students likes to think about this one is, if you take people and you just throw them all into a bin and they're all bouncing around everywhere, order doesn't matter. So I'm just grabbing these people, 5 people, and they're all in the bin and they can go anywhere, it doesn't matter. If you take them and you pick them, you put them in specific spots. You are going to wash the dishes, you're going to man the door, you're going to do the sweeping. Then order matters. This one is all the same task, order doesn't matter, it's a combination. So this one was 12P5, this one is 12C5. So it's going to be the same first part. But now it's a little chaotic. We have to divide out the duplicates. So we're going to divide by 5 times 4 times 3 times 2 times 1. 1 for every one of the numbers up above. Right? Because I picked 5 items. How many ways can I arrange 5 people? 5 factorial. And did you get answers for those yet or not?
Yeah.
Where do you guys
First
get-
one is 95,040.
And this one should be smaller.
792. Sorry.
792. Good.
Yeah.
Good. All right. The last one is a little bit tricky. So this one is I want to pick, but I need to have exactly 2 men and 3 women. Order doesn't matter because they can do any task. But I need exactly two men and 3 women. So I need 2 men out of how many men?
7,
And I need 3 women out of how many women?
5,
5. So I need 2 out of 7 men,
Men.
and 3 out of 5 women. So find those separately, and then can I have 2 men or 3 women, or do I need to have both?
both.
Both. So ands we
Multiply.
multiply.
7 choose 2 times 5 choose 3.
Yep. 7 choose 2 times 5 choose 3.
210.
Yeah, 21 times 10, 210. Because this first number is, this is the number of ways of having 7 men and picking 2 of them. I can pick these 2 or those 2 or those 2 or those 2. And then for every 2 that I pick, I could pick 3 women, those 3 or those 3 or those 3. There's 10 different ways of doing that. So these 10 ways, as soon as I pick 2 different guys, I have another 10 ways of picking 2 women. Right, so it's 21 times 10. And you kind of look at, where is that? You kind of look at the, right, so it's sort of that thing like, yes, there's 21 ways of picking the men, but for every one of those ways, I've got 10 ways of picking the women. So it's, you know, kind of these, how many groups of 10 do I have? 21. All right. Do the next one. Should be really quick. Booty code. It's also a counting one. How do you know it's counting? Whenever it says how many, then you know it's going to be a counting one. Here, can we reuse items?
Yes.
So it's not a permutation or combination, because we can reuse items. How many choices am I making? How many decisions am I making?
6.
6. I've got a security code made up of 4 digits and 2 letters. How many options for the first digit?
10.
10.
Yeah.
Second digit?
10.
Next digit?
10.
Next digit?
10.
How about the letters?
26.
Uh-huh.
26.
And 26. So what am I doing these numbers? Multiplying them. Good. All good? Okay, great. Why don't you guys swing on down and do next page, E13. So the first part, what's probably someone likes broccoli?
51 out of 100.
Yep. There's 51 people like broccoli out of 100. So 51 out of 100. What's probably they're a man or a child?
73.
Nope, man.
I got
There's 38
60.
men,
38.
and there's 22
Oh,
children.
Sorry, 60.
I got 6.
Yeah, so 60 out of 100. Good so far?
Yes.
What about a child or likes broccoli?
That was 73.
Yeah, almost. So child, there's
no.
22 children, and liking broccoli is 51. But
Subtract the
note
overlap.
that there's this overlap here that's in both groups.
Right.
Right, so we have to subtract out the overlap of 10 because it's getting double counted. So that's 63 out of 100. Good? Good that we're reviewing this? How about okay, so dislikes broccoli and is a man, is that the one you're thinking about?
Yes.
Okay, so yeah, ands we do multiply. Great, so dislikes broccoli. So what's probably someone dislikes broccoli?
Is that 20? Oh, someone just.
Or
40.
probably they're a man? Okay,
Oh,
okay, we do that. Which one do you want to do first?
either's fine. So, man.
Okay, great, man. So 38 out of 100.
Mhm.
So this is probability of man. Okay, so let's do this better. Probability of man times probability of broccoli, but man has already happened. Do you guys see what I'm saying? If we say probability of man, then it's broccoli given man. So So if we're gonna do both, probably man times probably broccoli, given that man has happened. So this would be, what's the probability of man?
38.
38 over 100. What's the probability of broccoli given man? So knowing it's a man, so if you know it's a man, what's probably, means it's not a woman or a child, but if you know it's a man, then it's what? Probability of broccoli is 17 out of 38. You see what I'm saying?
Is it 20?
Well, this dislikes broccoli.
Oh, sorry, 21. Dislikes broccoli. 21 out of 38. So 21 out of 38. And look how nicely these 38s cancel out for me. So I get 21 over 100. Now, you could have just done it the easy way. How many men dislike broccoli?
21.
21 out of
100.
100. So you can do either one of those. The and does still matter. If you're caught on the and means multiply, yes. But you got to remember it means multiply with you have the first one and then do the second one given the first one's happened.
Makes sense.
Yeah, this one, if you have a table, it's just so easy just to grab the min and broccoli, 21 out of 100. And the last one is so the given one, so that's, was it women given, is it broccoli given women?
Likes broccoli given she's a woman.
Broccoli given women. So again, remember this given means that woman has happened, which means that you know it's not the man or the children, you're talking about this one right here. So what's the probability that they like broccoli? 24 out of 40. 24 out of 40. Given woman means you know it's a woman, so you know it's got to be one of those 40. Given's the only time when you change the denominator. The denominator should be 100, it should be the total every time, except for that. And a lot of people don't remember what to divide by, right? So if you think of it as broccoli divided by women, the women is what's on the bottom. Okay. And the last one was independent. Are broccoli and women independent? So remember, this independence is all about proportions. Chapter 12 was all about proportions. So is the proportion of likes broccoli the same as likes broccoli given women? So those four numbers, are the ratios the same? So in other words, is 24 over 40 the same as 51 over 100? No. So dependent. Does that make sense? Or you could just compare the probability of broccoli given woman to the probability of broccoli given nothing. Which is this? This is the probability of broccoli given women. This is the probability of broccoli given nothing at all. And are they the same? No, they're not the same. So they're dependent. Mutual exclusive is, if you guys remember, it's like if I'm mutually exclusive and you're mutually exclusive, like I'm not going to mix with you. I'm exclusive of you and you're exclusive of me. We have nothing in common. So two things that have nothing in common are mutually exclusive. Are broccoli and women, are there any people who are women who like broccoli? So they have some people in common, so they're not mutually exclusive. Okay with that part?
Mm-hmm.
All right, why don't you guys do the next one down? 12?
14.
14? Oops, 14. That'll be our last one. So draw a tree. Have to. All right, so let's go ahead and draw. So how many options do we have for the first draw? Yeah, red, blue, green. And what's the probability of each of them?
2 out of 11,
Uh-huh.
4 out of 11, and 5 out of 11.
Great. Now, when you draw something, these out. She's coming. Say I have these pens, and she's going to take a pen, and then she's gonna take another, she's also gonna take a pen. Would she take the same pen?
No.
No, I mean, if you're gonna take something and have it, you're not gonna take the same one as somebody else. Does that make sense? And that's gonna be true on the exam as well. When someone takes one, someone else is gonna come along and take theirs. Right, okay, good deal. So here, you're drawing a marble, you're not replacing it, you're keeping it, and someone's gonna draw another marble. So this is without replacement. Everybody on board with that part? So then, what's the probability of I could get a red, blue, or green. Here I could be a red, blue, or green. And here, red, blue, or green. Sorry, I got all this stuff. And make sure that you guys have this is your destination. I did a red, the end of the destination should be green, the very end of the line. Along the line is where you put your probabilities. So what's the probability, if I drew a red first, what's the probability I draw a red the second time?
1 out of 10.
1 out of 10. Because now there's only 1 red marble left and only 10 marbles total. How about blue?
4.
4 out of 10.
Green?
5 out of
Great. And then if I drew a blue one first, I have for red,
10. 2 out of 10.
for blue,
3
3
out
out of 10.
and for green.
5 out of 10.
Great. And then the last one,
2 out of 10.
2 out of 10,
4
4 out of 10.
and then 4
4 out of 10. Great. So let's answer our questions. First draw is either green or red. Or as we add, so green ones or the red ones, I've got 2 plus 5, 7 out of 11 chances of being successful. How about blue then red? And blue then red means I draw a blue one first, and then I draw a red one. So it's kind of like and. It's another way of saying and. Good. Like if someone says she went to the store, then she went to home. She went to the store and home. She did both of them, right? So and we multiply. So we're going to follow along our path here. Blue, then red means we go along there. And again, as you go along the path, along these trees, you're going to multiply them. So 4 out of 11 times 2 out of 10. So 8 out of 110, and you can just leave it. You don't have to reduce it. Just leave it like that. That's fine. Okay, cool. And then your next one, your other question was, what was it?
Green on second, given blue on first.
Yeah, probably green on second, given blue on first. So this means that I'm given blue on first. What's the probability I drew a blue one first?
5 out of 11.
100%.
4 out of
I'm given blue is on first. The probability I drew a blue on the first one is 100%. It happened.
11.
So here, I am standing right there. This happened. I'm giving you that. I'm saying, I drew a blue one first. That's information. You know it's happened. 100% I'm here. What's probably I draw a green one?
3 out of 10. 5 out of 10.
5 out of 10.
Can't read.
Yep. So that's your answer, just 5 out of 10. So probably green on second, given red on first, is 5 out of 10.
Blue on
Straight up, that's it. Good?
Yep.
Okay. That is it, because you guys did the other problem earlier, right? The hypothesis test?